I think we can make a start. Good evening, ladies and gentlemen. A couple of housekeeping points. The fire exit is here, and if you could just please ensure that you've either switched your mobile off or put it on to silent. Welcome to the Geological Society of London, and to this, the 5th 2016 Society London lecture, entitled What Coal Mining Hydrogeology Tells Us About the Real Risks of Fracking. My name is Leif Carroll, and I'm a council member and trustee of the Geological Society, as well as incoming professional secretary, and a chartered geologist as well, for my day job. And it is my pleasure to introduce today's speaker, Professor Paul Younger of the University of Glasgow. Development of shale gas by hydraulic fracking, is opposed by campaigners who fear that groundwater supplies could be polluted. There are strong reasons for doubting this. In fact, shale gas developers and environmental guardians have a common interest in avoiding interconnection to aquifers, for which there is a century-long analogue, namely longwall coal mining beneath the sea and major aquifers. To explore this with us today, we welcome Professor Paul Younger. Paul Younger holds the Rankine Chair of Engineering and is Professor of Energy Engineering at the University of Glasgow. He was formerly Pro-Vice-Chancellor for Engagement at Newcastle University, where he also established and led the Sir Joseph Swan Institute for Energy Research and subsequently the Newcastle Institute for Research on Sustainability. A geologist by first degree, Paul trained in hydrogeology in the USA as Harkness Fellow in the mid-1980s, subsequently developing a career in environmental engineering. He is a Fellow of the Geological Society and a chartered geologist, as well as a chartered engineer. He was elected a Fellow of the Royal Academy of Engineering in 2007 and has received honorary doctorates for his mine water pollution work from universities in Spain and South America. Paul has founded and directed 4 companies in the water and energy sectors and has authored more than 400 items in international literature, including several well-received books. His knowledge of shale gas was gained through serving on the Joint Royal Academy's expert panel, which reported to the UK government in 2012, and on the independent expert panel on unconventional gas, which reported to the Scottish government in June 2014. Ladies and gentlemen, please welcome Paul to the stage.
Well, good evening, ladies and gentlemen. It's always a great pleasure to talk in this particular venue. This is my first and dearest professional and academic affiliation to Geological Society, and I've never really lost the thrill of speaking in this particular splendid building and this splendid lecture theatre. Though tonight I'm going to have to, I'm told, behave myself a bit more than normal, because I'm one of these guys that tends to run around the stage and do silly dances and sort of wave my arms around and. But this is being live streamed and filmed, so and I need to be near these microphones. So those of you who have seen the antics before, I'm afraid it's going to be a bit more boring tonight. Those of you who've never seen them, well, you're lucky. So I'm going to have to go at some speed through this slide set, because I've first of all got to assume that not everyone in the audience is at the same level on the story of shale gas fracking in particular, so we'll have to give some background on that. But before I do that even, just to say, by the way, almost everything I'm saying tonight has recently been published by the Royal Society of Edinburgh, complete with all the references and all of that stuff, and it's gold open access, so you can have the whole paper for free. Just click on that web link. I think it's on the handout you've got anyway. So before I get on to fracking, I'll have to say a bit more about gas in general. What's the issues with gas in the UK? And that'll be gas. And then I'll talk about how shale gas fracking is done. And then I'll get on to kind of a sort of generic risk analysis, if you like, at the top level, and develop this analogy with coalfield hydrogeology, and in particular a case study of the Selby coalfield, where I did quite a lot of work quite some time ago now on the hydrogeology in the run-up to the closure of that coalfield. And then I'll have one slide right at the end which summarises what I think are the true risks of of shale gas fracking when we're done with all of that. So hang on to your hats. I'm going to have to go at quite a pace to get through all these lectures on any reasonable time scale. So the first thing to talk about is the UK's ongoing addiction to natural gas, which we adopted in a well-coordinated national campaign to convert us from town gas to North Sea gas, the sort of technology change that government now finds just about impossible to organise, apparently. But back in happier times, we got everybody off town gas and onto natural gas in a very short period of time, concerted effort, tweaking the technology, and we've all been happily using natural gas for decades now and taking it for granted, also taking for granted the cheap energy that it represents. So we pay generally a lot less for our energy in this country than people are used to in other countries in Europe that are not blessed with indigenous gas resources. And the politics around that is a bit weird because our politicians keep on telling us that we're going to get greener, but we're going to get cheaper as well. And it don't quite work like that. It doesn't add up like that. But anyway. So the first thing to say about gas is, well, yes, it's a fossil fuel. So, you know, like all fossil fuels, we use it, we emit CO2 to the atmosphere. This is bad for global warming. So we definitely want to use less fossil fuels. But if you look at this table here, from the real bad boy at the top, Lignite, and Germany is keeping its lights on by a dash for Lignite lately because they've outlawed unconventional gas for the time being. It's a far better idea to go from coal use to gas use than from coal use to lignite use, as you can see from this table. If you go from coal to gas, you more or less halve your emissions straight away. So a shift from intensive coal-fired combustion for power, and certainly for domestic purposes, the transition we made some time ago, to gas is a step in the right direction of decarbonisation. But obviously these figures for the unabated emissions of using these fossil fuels, they're still quite horrendous compared to the emission rates for the various renewables listed below in Suitably, Virtuous, Green. But if we were to apply carbon capture and storage to the fossil fuels, which would take the cost of the energy to about that of the mainstream renewables, actually, would take into about the cost of onshore wind, then the emissions scenario changes. And the green bars here are showing more or less what was on the last table now in graph form. The yellow bars are where you get down to if you apply carbon capture and storage to those various fossil fuels. And what you'll notice is that natural gas gets surprisingly close to solar PV in terms of its overall emissions if we went for it and, you know, insisted on carbon capture and storage. And the cost would only be similar to what we're committing to for Hinkley C and what we're committed to already for onshore wind. So it's something we can afford, but it's a political football. So, you know, the government would rather not go there and has recently cancelled what was left of the UK's ambitions as regards a CCS demonstrator. A very lamentable decision from my point of view. I think it's something that will come back to haunt us, but that's a whole other lecture. Now, when we're talking about gas, people normally miss that the big use of gas actually is this. You know, it's easy to point at gas-fired power stations and say, look, there's a big use of gas. Actually, the big use of gas is the 82% of us who rely on it for central heating, hot water, and cooking. So the humble domestic gas boiler, add them all together, that's 2/3 of the gas used in the country. 82% of us, as I say, rely on it. That's the lucky 82%. Okay? If you're in the 18% who have to use fuel oil or electricity because you're not connected to the gas grid, you're 4 times as likely to be in fuel poverty. Okay? So just to say, globally, we're going to electrify all heat, and that's the end of the carbon emissions problem because we're bound to have decarbonised all electricity shortly. Watch what you wish for, because almost certainly you're going to push fuel poverty up through the ceiling if you do that. So you've got to be careful what you wish for with some of these very simplistic solutions, even if it were the case that not only are we going to replace all use of fossil fuels for current electricity production, but we're also going to quintuple electricity production to provide heat and transport fuels. It's not going to happen, okay? The scale at which we would have to do that is just breathtakingly enormous. people get confused about energy use. Okay, the largest single end use of energy in this country and in most countries of Northern Europe and North America and so on is non-electrical heat demand. In the UK as a whole, it's 40% of end use of energy is for non-electrical heat demand. Electricity is only about 20% of final energy use, and the balance is transport. In Scotland, it's even more marked. It's 55% of final energy use is heat. And again, more than 80% of that is gas. You know? So just remember, the big use of gas is the one for which we're all responsible. And if you really hate the idea of unconventional gas, get rid of your gas boiler, but prepare for fuel poverty. Now, we also use gas to balance the electricity grid. So this is electricity demand here, typical daily electricity demand profiles for winter and summer for the UK as a whole. So the left-hand axis there is in gigawatts. And you can see that in the depths of the night time, obviously there's not a great deal of demand. Then we wake up in the morning and breakfast and so on, it ramps up, sets down to a dull roar while we're all at work. Then we come home exhausted, put the telly on, put the microwave on, put the oven on or whatever, and demand shoots up about 6 o'clock. And then it starts to ease off through the evening with a more sharp decline as it gets near closing time in the pubs. And then settles down to the low value through the night. Now, the way we cope with matching electrical output to this demand, you might say, well, the easiest way to do that is storage. That would be the case if we had lots of storage options that were remotely affordable. The only one we've got that's affordable at the minute, and that's somewhat marginal, is pumped storage hydropower. But if we were going to do the work that switching on and off gas-fired power stations, and until recently, it's tailing off now, but coal-fired power stations also have this ability to flexibly match the demand. If we were going to do all the storage to replace their duty, we'd need something like 200 pumped storage hydropower systems of the size of Dinorwic. Some of you will know Dinorwic in North Wales. We don't really have that many upland valleys that we can flood. Certainly not without strenuous objections from environmental activists, including myself, actually. I don't want to flood 200 upland glens. I've got other uses for them, such as nothing, such as just going there and having them as upland glens. Anyway, so what we do to meet demand, we blend our technologies, okay? So we join all the minima on the demand curve, and the straight line that joins the minima, we call that the base load. And there are certain technologies that are good at base load. So the fossil fuels are good at it. They can sit and chug along at a constant rate. Nuclear can only do that. Nuclear outputs at a constant rate. So it's a very good base load technology. It can't track demand. But it's good at base load and it's low carbon, definitely. You often hear that disputed, but it's shown beyond doubt. But like a lot of other zombie statistics in the energy area, it doesn't matter how many times you kill it, it keeps coming back. And superimposed on the base load, we've got the fluctuating demand over time. And the way we've met that, as I've said, historically has been with coal-fired and gas-fired power stations, because you can crank them up and crank them down over a time scale of 20s or 30s of minutes. The renewables sit somewhere in the middle of the graph, so we have to wrap the other things round them, because the renewables, by and large, with the exception of pumped storage hydropower, but we've only got that in small quantities, the renewables, by and large, are not so dispatchable. Biomass combustion, yes, which is mainly being done by former coal-fired power stations. So getting this right is difficult unless you've got, in particular, gas. Gas is very good for doing the dispatchable bit of this curve. So we can dispatch the power on demand. And it's worth remembering as well that gas is not just for energy. So here's the Grangemouth complex. I could equally have put the Teesside complex or the Runcorn complex or other complexes around the country where the chemicals industry are. Almost all of the synthetics that we rely upon, the transport fuels and the plastics that we use, so much that's on this table in front of me, comes originally from petrochemicals. Often the clothes we wear. The fleece jackets that you wear to stand on a picket line saying that we shouldn't have fossil fuels, made out of petrochemicals, ironically, But they're normally a nice green colour, so it feels all right. Gas is also an industrial feedstock, and we get rid of these last remaining process industry clusters at our peril, because the UK has not had a positive balance of trade since the 1980s. The regions that have these clusters are the only parts of the UK that have a positive balance of trade. If we get rid of them, we're going to plunge the country further into its negative balance of trade. We're living in a fool's paradise in the UK, where private debt is even greater than the national budget deficit, and this is all to do with strange attitudes to whether we should pay our way in the world or just pretend, because GDP counts things like consumer spending on tick and house price inflation. These all contribute to GDP, and we kid ourselves that this is somehow economically beneficial, and we've insisted on successive governments that feed that fiction, so we can't really blame them. We elected them. We don't question them very closely. But, we dispense with all of this at our peril. And if we don't have affordable sources of gas, this stuff is gone. Okay? And our balance of trade is going to get worse. So we have, of course, had the luxury of the North Sea, and to a lesser extent the Irish Sea, for several decades now. Most of the fields offshore in Scotland, oil with a bit of gas. Most of the fields offshore England, gas with very little oil. This is to do with the relative depths of burial and the burial and exhumation histories, why one's predominantly oil, one's predominantly gas. The fact that England has an offshore industry tends to be news in Scotland, by the way. They think they've got all of it, and there's a very bullish about it, and there's nothing in the North Sea that's not theirs. But this map is a sort of a good sort of reminder that it's not quite that simple. But there's as I say, it's was it P.G. Woodhouse that said it's never too difficult to distinguish between a beam of sunlight and a Scotsman with a grievance. Anyway, UK gas production from these offshore sources peaked around the millennium and has been in steep decline ever since. And that decline has continued. I've struggled in vain to find a more up-to-date graph from DEC. I think it's just so embarrassing and depressing that they haven't put it on the web anywhere that I can find it. But rest assured that steep decline has indeed continued since 2011. And so if that's going to carry on, and we're going to carry on using gas at more or less the rate we're using it, we've got a problem. Okay? So we were accustomed to a rising trend of gas production till the turn of the millennium, very steep decline since. Now this is the National Grid's estimate of how, even if we manage to do the most green things we can think of in our energy balance, in domestic heat, in dispatchable power on the electricity grid, this is the most green scenario for how much gas we're still going to be using by 2030. Okay? So this is the optimistic scenario. And you can see that if we're as good as gold, by 2030 we may have shaved an impressive 25% of our total gas use. Then again, we might have shaved nothing of it. Okay? Because we're doing away with other sources of dispatchable power, and there's no great shakes happen to displace gas out of domestic heating. So the reality is probably a lot less than that. So we're going to be, even on the most optimistic, greenest scenario, we're still going to be very heavily dependent on gas long into the future. Now, if our gas demand continues and our domestic production declines, we get an import requirement. There's no other way to do it. So the faint line at the top is demand, again under the gone green scenario, the most optimistic green scenario. The darker line at the bottom is projected UK production with certain assumptions built in there. And you can see the gap between the two is the import requirement. Now, we can either, and by the way, just remember all of this is the best case scenario. Yeah? There's only one person I know who's really chuffed about this scenario. Yeah? At the minute, we import most of our gas from Norway, but they've got the same decline problems we have. We're starting to import LNG from Qatar, that's liquefied natural gas from Qatar, in tankers. at about twice the carbon footprint of domestic gas. So that gets it about back to where coal was. It takes as much carbon to get the stuff here as the carbon that's released by using it when we get here. So relying on LNG from distant countries, not a good idea if you care about carbon emissions. Pipeline from Russia would have a similar carbon emissions requirement, but hey, what's that between friends? And you know, when we become totally dependent on Russia in due course, if we follow the path we're on, of course there will be no political price exacted by Putin and his heirs. I mean, you know, we'll be great mates with them by then. And they wouldn't dream of doing anything to us like they've done to Ukraine in the past, holding countries in that part of Europe to ransom in the middle of winter, switching the gas off and seeing the ensuing political chaos. They wouldn't do that to us, would they? No, not at all. So, how about indigenous gas? Given that we're not doing anything to get ourselves off the addiction, you know, it's a bit like you could maybe solve America's drug wars by domestic production of coca and, you know, poppies instead of bringing them from South America. But nothing's been done to address the addiction. Yeah? So one way of addressing the import requirement and reducing the geopolitical risk that goes with it, as well as the carbon emissions and the cost of importing gas, is to look at indigenous sources, of which shale gas is one of them. Okay, we could talk for a while about other sources, biogas, underground coal gasification, coal bed methane. We haven't really got time for all of them. So shale gas it will be tonight. That's the one that's been most controversial. So we might as well stick with that anyway. Now, just a few wee cartoons to show how the shale gas process works. So you've probably heard by now that it involves directional drilling so that you end up with long lateral sections of boreholes, maybe 1 kilometre or so, running through a shale bed. And just to remind you, as a hydrogeologist, it is my duty always to do this, that the subsurface, apart from a wee bit right near the top, is pretty much saturated with water. Okay? And that includes these shale beds, but the water in the shale beds isn't going anywhere. It's been sat there for millions of years, if not hundreds of millions of years, doing nothing because there isn't really the permeability in the driving head for it to do much. So we drill down, we have this well deviated, then we inject water and certain additives, which we'll come on to later. We pressurize these up till they overcome the compressive stress at that depth, and fractures form. Now, the first thing I have to say is that this is ridiculously not to scale. Okay? If this was remotely to scale, you wouldn't be able to see the well, and you certainly wouldn't be able to see the fractures. Okay? So I have to point that out. If I drew this to scale, it would look like the original slide without the well. You know, it would just be a blank piece of rock. I mean, this really is a very small part of the sequence that's been affected by the fractures. But in every diagram you see on the BBC, it's similar to this. And I have some sympathy because, you know, we do slides in landscape format. If I was going to do this to scale, the slide would have to run down and all the way through the library and somewhere at the far end of Piccadilly, you know, it would be roughly where the fractures were, you know. And I have to drag you all out in the rain to look at them and then bring you back in. So I can understand why it's not done to scale, but you do need to remember that. So the process involves injecting a mixture of water and various additives. This is the other bit where the shale gas revolution started. So one thing was the drop in cost of directional drilling. We've been able to do directional drilling for a long time, but it's been very dear till relatively recently. The cost of it came down quite significantly in recent decades. The other thing was, if you fracture a shale, and anybody who's ever been on a field trip would know this, and especially anyone who's ever been down a mine would know this, you fracture shale, it has a tendency to heal up again. Okay? It's very soft stuff, bendy stuff, you know. It'll tend, any fractures you make in shale will tend to close up again. Then someone had the bright idea, what if we prop them open? So the most important additive in the fracking process are the sand grains you can see there. Just the ordinary sand that you see on the beach, okay? Nothing sinister, just ordinary, everyday, common or garden, or common or beach sand. And they have the effect that when you've got these fractures to open temporarily, you put some sand grains in, and then when they try to close, the sand grains prop them open. So you can do it with other things. You can do it with sort of ceramic beads and things like that. And they're all rather grandly called proppants. So something that props something open. So these proppants hold the fractures open. Then, having pressured it up to get the fractures to work, to propagate, you've then got to depressurize the whole system. You've got to get any water you injected out, plus any water that it picked up while it was in there, and you've got to get a pressure gradient into the well. Otherwise, the gas will never come out the well. So it turns out that in terms of the shale gas process, it's only at high pressure for a period of time of hours to days. Throughout the production period, it's at much lower pressure than the surrounding rock. Okay? And that period will persist as long as the well is in production, so years to decades. Okay? In the few hours or days that the well has a positive pressure, where it has a greater pressure than, for instance, the water table would be at surface, there's no hope that water can flow up through a couple of thousand meters of very low permeability material in the time period of a few hours or days. Just Darcy's law, basic stuff, cannot happen. Okay, there's just not the time. In the period when the well is in production, the hydraulic gradient is always into the well. Okay, and I'm gonna labour this point because it's always overlooked, and it's the most crucial point in understanding why the groundwater risks are not as they've by and large been portrayed. So we've pumped the water out of the well, lowering the pressure in the fracked horizon, though note the surrounding rock mass is still pressurized. Okay, there's still water everywhere else, it's just the fracked horizon we've drained. And then finally the gas will come out, but only as long as you've pumped that right down and you've exceeded the bubble pressure of the gas that's really loath to come off these shales. It's been there a long time without moving. So that's kind of how it's done, okay? And just bear in mind the scale issue. Now, we've been talking about the North Sea oil and gas, and we're conscious of this idea that there's a lot of wells offshore. What's news to a lot of people is that we've actually had about 2,000 onshore oil and gas wells, okay? Scattered, throughout the country, quite a lot of these wells. And so it's not completely new to do onshore oil and gas exploration in the UK, and a lot of these wells are still producing, okay? Most people don't even know they're there. They're pretty good neighbours, these existing wells. Once they're in long-term production, there's a little pump at the head of them. Sometimes they're celebrated. There's a pub in Nottinghamshire near one of these that is called Ye Oldie Oily Welly or something like that, and it's next door to one of these modern donkey pumps, and people are quite happy to sit outside with a pint and look at this thing and say, the good old days of conventional oil drilling in Nottinghamshire, them were the days, So we've had quite a bit of onshore oil and gas. This is probably only about the 10th of the number of wells we'd need for shale gas to be a significant part of the energy future, okay? So we'd need a lot more than this for shale gas to make a significant impact. But 10 times doesn't sound like that many for something that most people didn't know was there at all, to me. And of these onshore oil and gas wells, about 10% of them, so roughly about 200. We don't know for sure because there hasn't been any requirement to record this until very recently. There's been no regulation, and the government have not gathered statistics on it. But from what the companies tell them, about 10% of them have already been fracked, going back some decades, without a single one of them ever causing any problem. Okay, so it's not like we've got no experience of this. We do. Not one of them has caused a problem during production or after abandonment. This has not been, you have to look long and far to try and find some problems. And when you find something that you might talk up as a problem, it turns out to be the square root of bugger all. But, worth saying as well that fracking is not just used in oil and gas. I'm a hydrogeologist, and from time to time we use fracking for water wells. So any of you ever been to the Highlands of Scotland? And if you have, and you've hired a cottage there or stayed in a small guest house, you'll have had that experience. You've had a good day on the hills. You need to have a bath and get cleaned up and, get restored before you start drinking far too much whiskey. And you go and run a bath. And then you go in and you see it's the colour of Newcastle brown ale. Right? So it's brown water. And brown water's been consumed for, centuries in the Highlands. Nobody's had any bother with it. But there is a theory somewhere in the European Commission that if you chlorinate this peaty water, not that they would know because Scotland's about the only place that has it, it might form chloromethanes, and then there's another might beyond that. The chloromethanes might be carcinogenic if it's all you drink for all your life. So on that basis, they've outlawed brown water. Right? So they've suddenly got to find crystal clear water in the Scottish Highlands, and I have to tell you that the bedrock in the Scottish Highlands is not very obliging. So if you want to get crystal clear groundwater that's had the brownness, the humic and fulvic substances filtered out of it by filtration and circulation through the subsurface, the only way you're going to get enough permeability is to frack. So we frack the bedrock in the Scottish Highlands, and the result is that villages such as Lagan Bridge and Allegan now have crystal clear water, where previously they only had brown water. And this is down to this intrinsically evil, unintelligible process called fracking that we've been doing for years. But of course, the whole thing, as you know well, has descended into polemics, to frack or not to frack. And obviously, it's got very emotive. Stop poisoning our future. Frack off, normally followed by another noun that I won't repeat in polite company. And, the whole thing's got completely polemical, hence it's a polemic. I think the roots of this controversy do not lie in the UK. Okay, so I'm going to tell you why I think this thing got so polemical so fast. Why did it get so out of hand? Now, in the United States, there are many fine things about the political system of the United States I greatly admire. I lived there for 2 years. Okay, I really like their federal system, and I really like the way that that's set in stone, and the duties of and responsibilities and so on of the individual states and down to the county level are inviolable. Their relationship to the federal government, there's a good structure, and there's participation and democracy at the local level and the state level is really quite healthy in the States. But certain aspects of the politics in the States are weird for British eyes, and they have this sort of pork barrel system of politics. One aspect of the strangeness of some of the nooks and crannies of the American political system is, if you are ever, it's an unlikely contingency for those of us here, I grant you, but if you are ever elected Vice President of the United States, then in a show of sympathy from your fellow politicians who tend to recognize that unless you happen to be Vice President at the time Richard Nixon is in office, that's the pinnacle of your career. There are very few people go from being Vice President to President. So as a consolation prize for having peaked out just before the top job, you're allowed, after you're appointed as Vice President, one law through Congress unopposed by the entire House. Now, when it was Dick Cheney's turn, he also had on his CV Vice President of Halliburton, the world's largest oilfield services company. So he chose, for his special act of Congress that went through unopposed by Republicans, Democrats, or anybody else, not that there is many other else, he had amendments passed to the USA Energy Act 2005 that basically said that the then nascent shale gas industry was exempt from almost the entire environmental rule book. If you read the paper, you'll see the details of what he got it exempted from. It's breathtaking. Okay? Now, this had two consequences. One was every cowboy in the country, and of course there are a lot of cowboys in America, every cowboy in the country who had a drilling rig suddenly resprayed themselves as a shale gas driller and went out yee-haw, gung-ho, and we're gonna drill and frack, and to hell with the environment, because we don't need to bother with the environmental rule book, so we'll dispose of our drilling fluid how we like. We'll fling the cuttings over there. We'll let the cattle, drink the drilling fluid, and we don't mind what we spill. We'll not bother too much if we spill some diesel and some oil and so on. So all this sort of stuff went on. This is going to happen if you unleash the inner cowboy in a country like America. Would happen if you release the inner cowboy in the UK as well. Which is why we need environmental regulations that do not get exempted for any industry at any time. The other consequence was that quite reasonably, for the people who weren't having the bonanza from suddenly doing this in a sloppy way, so most other people asked themselves the question, if shale gas needs these exemptions, what's wrong with it? Surely it must be dreadful. If it needs this level of exemption from environmental laws to get anywhere, it must be really awful. I think that was a big disfavour to the industry because it's not so different from conventional oil and gas. And I don't think it did need those exemptions, but the cat is out of the bag. And the era we live in, you won't struggle to recognise this. We're in the era of social media. So add that to this scenario, and you've just cooked up the perfect storm. And all of the scare stories, horror stories, anecdotal instances of stuff that on close inspection and a bit of isotope analysis invariably turn out to be wrong. All of these horror stories cross the Atlantic before anyone here even reckons we might have any shale gas to go for. And, it's already alarm, legitimately so, on this side of the Atlantic, about the prospect of this sort of cowboy-style bonanza happening here. But, there's a big but. No one here ever said we're going to relax a single environmental rule. In fact, we're making stricter environmental rules for this industry than apply to other existing industries. There's a huge difference. So there will be no cowboy bonanza. It remains to be seen whether it's going to be viable at all. Until such time as someone drills and tests a few wells in our shales, we won't know. So this might all be a fuss about now. Might very well be a fuss about now. But anyway, the protesters have eloquently stated their concerns in a number of cases. And this diagram I love, look how mucky it is, right? And those of you who've got a gas-fired boiler, next time it's running, pop outside and have a look. And let me know if there's a lot of soot coming out the flue. As if there's something radically wrong, and it means you're burning something other than gas. Okay? You do not get soot, like is shown on this diagram, from methane. But it's done for a purpose, and also they've also got this greatly compressed vertical scale. So we've got all sorts of things we might worry about, but the one I'm going to focus on tonight is precisely this, that the fractures propagate upwards. They intersect the freshwater aquifer, which is now full of soot for some reason. I don't know why, but it's full of soot. And it's set a well on fire, and it's polluted, and it's horrible, and, all of that. So what we're going to do is have a look at that. It's not the only concern they have. It's the one we're mainly going to talk about. I'll just do a brief breeze through some of the others, just by way of a little draw your breath before we dive into all the groundwater pollution detail for the rest of the lecture. So all of these issues have been addressed by two panels, and as was said in the very kind introduction, I served on both of them. And I do exhort you, these are freely available online, download them, read them. We went to some trouble to write them in language as we hope understandable as possible for lay readers. We do assume a certain amount of intelligence, but assuming a sort of average intelligence, we do hope that these are pretty readable, but they've not been read much. But all of these things have been gone through in detail in both of these panels. As regards induced seismicity, just a quick throwaway on this. This is a paper that my colleague Rob Westerway and I published in a journal of this august institution a couple of years ago, the Quarterly Journal of Engineering, Geology and Hydrogeology. And what we did is we looked at the government's hastily introduced rules on seismicity potentially induced by fracking, where they said if you have a local magnitude event in excess of 0.5, you've got to stop what you're doing and have a big inquiry. Okay. Now, nobody can feel a 0.5 magnitude event originating 1,500 meters below ground. Okay. In fact, let me demonstrate what a 0.5 event starting, that sort of depth, 1,500, 2,000 meters below ground, would be like for you to experience as the vibration, not the sound, okay, just the vibration. Are you ready? Hang on to your seats. I have the technology here to do this. You ready for this vibration? That was it. Anybody fall off their seat? I didn't crack the lectern or anything like that. So that's the level of vibration we just outlawed. So by that logic, we should definitely be outlawing buses, probably motorbikes actually. Definitely we should get rid of the underground immediately, far more vibration. And in fact, these rules that have been introduced are de facto 40,000 times stricter, 40,000 times stricter than the long-established rules on vibrations caused by quarry blasting. That, to me, doesn't make sense. And I think the nascent shale gas industry, if it ever gets anywhere, is going to find it very hard to live with that. Because, on a night after a powerful curry, I can produce a local magnitude 0.5 event, They're going to find that very hard to live with. But to try and appease the protesters, they kept their gob shut and said, yeah, we can live with it, They can't, but they'll figure that out too late. I got a death threat, by the way, when this was put out in public for pointing this out. So there you go. That's the level of debate we've got these days, sadly. Fugitive gas emissions, that's me in the corner. On one of my wells, I don't drill gas wells, right? I drill deep geothermal wells. I've got no link to shale gas. I have no interest. I have no shares. I don't care if it happens or not. All I care about is the misrepresentation of my area of science. And that's the only reason I bother with this. I don't really enjoy death threats. But I drill deep wells. So this is the one in central Newcastle that we drilled at 1,821 metres for geothermal energy. And of course, we have to take the very same precautions as an oil or gas well would have to take, because although we're drilling in an area where we're pretty sure we're not going to find gas, because that would be a bit of a disaster for us, we've got to take all the precautions just in case my usually flawless geological reasoning happens to be wrong. So we have the triple action blowout preventer. We have alarms all over the place. If any methane is detected at the wellhead, the alarms go off. Everybody's got to immediately leave the well, go to this muster point off site, and then send for the specialist to come and kill the well. Because if they don't kill the well and you hang around, you might get killed. But to hear the way this fugitive emissions is talked about, you would think that drillers don't want to get home alive at night, because the people in the front line of the explosions is the people close to the well, the drillers. And funnily enough, I never yet met a driller with a death wish. Maybe I haven't been around enough, but I never met a driller who has a blasé attitude and says, I tell you what, let's not bother powering up the alarms. If we get some fugitive emissions of methane, what the hell, we'll just crack on with it, because, I'd rather risk my life than inconvenience the company. Those people don't exist, okay? They don't exist. They're human beings like everybody else. And there's a wider issue of fugitive gas emissions. The greenhouse gas power of these things. A report done by colleagues from the University of Strathclyde. Again, you can get all of this online. The worst case scenario they found was if you developed a shale gas pad in an area with peat soil, removing the peat would have a negative effect on greenhouse gas emissions. But actually, that's what we do all the time for wind turbines. Wind turbines are routinely put on peat moorland. As far as I know, there are no proposals for any shale gas wells on peat moorland, for the simple reason that the shale gas basins are all much lower lying than that. Excessive use of water and wastewater disposal. To worry about this, you really have to believe that the Environment Agency and SEPA and Natural Resources Wales don't have the licensing system that is progressively developed since 1945. You would have to believe that there's no licensing of water use, no licensing, no consenting of discharges. But that's not true. We've got the most elaborate system. I used to police it myself. I used to work for the National Rivers Authority. A large part of my job was policing exactly those things. And it's very mature in this country. So if there's not enough water to do the fracking, it will not be permitted. If they cannot get rid of the wastewater safely, it will not be permitted. Okay, full stop. So they've either got to find ways of doing it that doesn't cause these problems, or it simply will not go ahead. That's our law. That's what will be applied. So the last one, groundwater pollution. I've left myself very little time to go through this now, as usual, with all my digressions. So we may have to overrun a wee bit. I hope I can crave your indulgence for that. So back to the ridiculously compressed vertical scale of this diagram. And the protesters are worried that if we frack here, fractures will go all the way up to this freshwater aquifer, and somebody out the picture will be abstracting that, and we'll have a very nasty surprise. Okay? Just to stress this thing about vertical scale, okay? Even the professional diagrams like that, the Joint Royal Academies have got this very vertically compressed scale, but they're showing everything from there to there. There's the fourth bridge for comparison, to give you an idea of how deep coal bed methane extraction has been proposed in Scotland and how deep shale gas has been proposed in Scotland. So it gives you a bit of a feel. This is a long way below surface. If there's any fresh surface water, it's all up here right at the top. Okay? Negligible difference from all the way to the surface. Huh? The fresh water doesn't circulate very deeply in these strata. Now, in groundwater assessments for anything, we use what we call source pathway receptor modeling to do risk assessments. What we say is, for there to exist a pollution hazard, there must be a source of pollutants, a body of pollutants of some sort. There must also be a pathway for those pollutants to get along a groundwater flow path to a sensitive receptor, which might be a freshwater aquifer. It's been used for drinking water, or it might just be connected to sensitive ecosystems, as many shallow aquifers are. But if we haven't got all three, we don't have a hydrogeological risk. You've got to have a source, a pathway, and a receptor. Quite a simple concept. And it's applied routinely, again, by the Environment Agency, SEPA, Natural Resources Wales, for instance. One of my favourite acronyms of all time, LUST. When I was a student in the United States in the mid-80s, I used to always go to conferences on LUST and proudly put them on my CV. Now you couldn't do it because of social media. People would get the wrong idea. Leaking underground storage tanks. And you can immediately think of a bunch of sensitive receptors. I mean, the groundwater itself is a receptor. If there's fumes coming off the top of the free product here, getting into the built environment, that's a sensitive receptor. If somebody's got a water well and it gets this stuff, that's a sensitive receptor, and so is this connected ecosystem. So we've got a source, we've got a pathway, and we've got a whole bunch of receptors. And we use this all the time, and we use it quantitatively. Okay? We haven't got time to do it for every conceivable site, not tonight anyway, but it would be done for every conceivable site in practice. Okay? But let's just run through what we got. So sources, what we got. We got the fracking fluid, okay? So this stuff is 94.6% water, 5.23% sand grains like you would find on any beach, and then 0.17% various additives. Most of these things are stuff that you would find under any kitchen sink. These are the fluids you've got beneath your kitchen sink for cleaning things, for disinfecting things, and they're not sort of something that was come up with in some lab by Dr. Evil. For which we have no COSH certificates, These things are so hazardous you can buy them in Asda. So that's the fracking fluid, but that's only pressurised up for hours to a couple of days perhaps, and then it's all removed from the hole and got to be handled safely at surface or it won't be allowed. When it's removed from the hole, it's changed in quality because it's washed out salt from the very old trapped salty water that's been there for millions, tens or even hundreds of millions of years in the shale, had a very long time to equilibrate with the minerals there, tends to be sodium chloride water, and that washes out with some of this injected fluid, and this is what we call the flowback waters. Now, these are not that scary either. We do have natural examples of these waters. In fact, here are some springs in the north of England, all very low flows, none of them have any impact on their receiving water courses. Where we have sodium chloride waters from depth reporting to surface. Some of which, basically the chemistry is pretty much like seawater. Okay? And a lot of them probably are modified seawaters from way back in the past. And like seawater, they also have a non-negligible concentration of naturally occurring radioactive materials. Now, the dissolved concentrations are never problematic, but if you put them through pipework and you get scale building up, they'll preferentially come out of solution and be in the scale. So when you finally come to get rid of the pipework, it might have a sufficiently high radioactivity count that it can't just be thrown away like anything else. It has to go to specially designated landfills that have a license to take that. But very, very low emissions rates and so on. Okay, so again, this is done routinely in a lot of industry, these naturally occurring radioactive materials. We're not talking about a sort of mini Chernobyl here, It really is negligible stuff and similar to seawater. So much for the sources. What about the pathways? Well, the pathway has three important factors. Firstly, you've got to have what I call hydraulic connectivity. You've got to have a way for water or gas or anything else to get from A to B. Okay? If you don't have that connection, that connectivity, then you can't have a pathway. But let's say you do. Let's say there's a fracture that goes all the way. Then that fracture has got to have sufficient permeability. In other words, it's got to be able to transmit enough fluid over a given time span to have a significant detectable delivery of the pollutant at the end of the pathway. We've got yet a third condition, even if that applies. That's that there has to be a head gradient that goes from A to B. If you've got a connection from A to B, but the head gradient is down from B to A, you don't have a pathway, okay? You have a way of drawing fresh water down to dilute the deep subsurface. You don't have a way for this stuff to get up. Only if the head gradient is upwards towards the freshwater aquifer, and the other two factors also apply, do you have a pathway, okay? Now, hydraulic connectivity, this comes down to fracture growth, and you remember the cartoon from the protesters, the fractures shooting up and going into the aquifer, okay, despite the huge vertical offset. Hydraulic fractures develop perpendicular to the axis of maximum compressive strain. When we're fracking, all we're doing is locally perturbing the stress field, but the existent stress field of the Earth is what dominates, and the fractures go up the parallel to the axis of minimum compressive stress. In other words, perpendicular to the axis of maximum compressive stress. Now a depth of 1,000, 2,000 meters, the maximum compressive stress is always going to be one of the horizontal axes, okay? So we've got horizontal maximum compressive stress. So any fractures formed at that depth will be more or less vertical, okay? But as you get close to surface, that changes, and the maximum compressive stress is the overburden weight, okay? So as you get closer to surface, the maximum compressive stress tends to be vertical near surface, and what that means is the fractures do that. They shoot off horizontal. So the geomechanics tells us that there's a built-in mechanism that tends to disfavor continued vertical connectivity of fractures, even if you wanted to believe for a moment that they're going to propagate over thousands of meters, which I'm going to show you in a minute isn't true. So even if they did do that, they're going to deviate. There's a lot of detail in there that we haven't got time to go into about how heterogeneous is the layered structure, what's the strength of the different layers, how do they refract as they cross soft and hard layers and all of that. We haven't got time for that. I haven't even got time for what I'm going to talk about. But there's been studies done of natural hydraulic fractures, that's the orange line here, this is just a histogram, and of induced stimulated fractures, and you can see that the induced stimulated ones pretty much, most of them are just like less than 100 meters, the odd ones maybe 200-300 meters, then they tail off. Natural ones from different geological processes. Again, I mean, the mode is further out, but it's still hundreds of meters, not thousands of meters. Okay, we never get here to thousands of meters. We just don't get there. Okay, so if we're fracking at 1,500 meters, 2,000 meters, we're just not going to get there with any fracture we could conceivably make. And in fact, that's very important to the people who run the shale gas wells, because if they create connections to the overlying freshwater aquifers, because they've got to pump all of the water out and keep it pumped out as long as the gas is going to come from the well, the hydraulic gradient will be down, and if they've created a connection to an overlying freshwater body, and I'll explain exactly what we're looking here at the minute, the water will be coming down and flooding their well, and they won't be able to pump it out because the well won't be a big enough diameter for them to have a pump big enough to shift the water. Therefore, the gas production will stop. Therefore, the well will be a complete failure. It will be drowned out. So the shale gas operators have an interest in not creating these hydraulic connections to overlying aquifers. And what we've got here is a large amount of data from a large number of frac stages in different wells in the Marcellus Shale, just stacked by depth from some of the deepest ones to some of the shallowest ones. The yellow line is the midpoint of the well for which the data is recorded. The red lines are from microseismic monitoring of how high the fracture is propagated. Very detailed microseismic monitoring is done to see if you've got enough fracture in the target shale. You don't want it outside the shale, that's a waste of energy. But you want to know that you've dominated the shale you're trying to produce from. And overlying these blue lines, this is the deepest penetration of the nearest overlying freshwater body, whether that be the base of a freshwater aquifer or the bed of a lake, the bed of a river, something like that. Okay, the nearest freshwater. And you can see that none of these fractures go anywhere near it, because if they did, it would wreck the wells. Okay, it's as simple as that. So that was hydraulic connectivity. Hard to get a sweat on about that. What about permeability? Well, mudstones or shales are some of the lowest permeability strata known to humanity. Okay, very, very low permeabilities by hydrogeological standards, less than 1 millidarcy typically. The surrounding unfracked mudstones even lower permeability. So the top value, the less than 1 millidarcy, that's after fracking. Okay, without fracking, even lower. And these are many orders of magnitude less than those typical of freshwater aquifers, like 1,000 millidarcy, something like that. If you have faults cut in the shales, the fault planes tend to fill up with shale particles and create a gouge that's low permeability. And the faults do not stand open because nobody's been in there putting sand grains to keep them open. So it is really hard to get concerned about the permeability factor. What about the head gradient? Well, just to reiterate this, we only have an upward gradient for a few hours to a few days during the actual fracturing process. Afterwards, the gradient is going to be downwards from shallow aquifers towards the shale gas, and therefore the shale gas operators have a confluence of interest with those interested in environmental protection, not to dare make an interconnection because it'll ruin their wells. Won't cause pollution, it'll wreck their wells though. Sensitive receptor, well, we could go on about this all night, but I think I've already said that the permeability, the connectivity and so on, that the pathway looks vanishingly unlikely, okay? Sensitive receptor, this is really polemical in Scotland. There's a moratorium on all unconventional gas now in Scotland, and catch me for a pint afterwards and I'll tell you all about that. It's a fun story, not particularly edifying. As Churchill once said, if you want to go on a liken two things, you shouldn't see how they're made. One is sausages, and the other is laws. Okay. Having been on the expert panel, I've had some insight into that. I'm still eating sausages on and off, but I haven't yet been to the sausage factory. So in Scotland, the big cry is, you can't possibly do this. It will pollute all of our shallow groundwater on which we so much rely for our drinking water uses. In Scotland, there's hardly any groundwater used, is the first thing to say. 2 or 3% maximum of the public water supply. But here's the real killer, okay? So the stippled areas, down here, up here, they're the few aquifers that are used for drinking water and irrigation in Scotland. The rest of the country, not used because the permeability is useless, okay? This shaded area is the principal area prospective for shale gas and shale oil. So not only would you have to buy it that these fractures are going to go up 1.5, 2 kilometres, the pollutants are then going to have to get on the circular line into Fife and get across the Tay Bridge or get on the West Coast main line and go down to Dumfries area or up to the Moray Firth if they're going to have any hope of polluting our aquifers. I think they wouldn't survive a ticket inspection. Now, for all of this paranoia, this is the crux of the lecture, really, and I'll try to get this over in about 15 minutes of overrun. I hope that if anybody really needs to leave, cheerio, but if you're happy to stay, it'll take another 10 or 15 minutes to do justice to this, I think. We've been here before on a much larger scale, okay? The UK coalfields are extensive, the longest history of mining in the world. We're the birthplace of carboniferous capitalism. Okay, we've been doing this for a hell of a long time. So we've learned a few things along the way, but as is our wont, we tend to forget history so that we can repeat it. But we've learned a lot from this experience. And indeed, mining has led to severe water pollution. So you think, oh, wow, why is he showing us this? You know, if you're from Quadrilla or something, you probably don't want this slide up here, right? Severe water pollution. I made my name, my reputation, all those publications that were mentioned, combating this stuff. Okay, so I know fine how this is caused. I know fine how to clean it up, and it ain't easy. Okay? Severe pollution. You're not going to get much worse. These are abandoned mines. Okay? Belting this stuff out for hundreds of years to thousands of years after mine closure. So mining definitely has caused pollution. So what the hell am I dragging this in for? Eh? There's another example. Ouch, look at that. Fordell Day level in Scotland. Ooh. A lot of really nasty water, acidic, high iron, high manganese, high sulfate. Definitely don't want to drink that, you'll have the runs. Well, you'll be sick first because of the iron, but anyway. Now, this is why I got into coal mining and hydrogeology, really. Firstly, it's a problem that afflicted my native region, still afflicts it, but nothing like as bad as it would have done had we not got involved and learned the hydrogeology, learned the geochemistry, figured out how to remediate these waters. And the hydrogeology of mines is fantastically complicated. We've created man-made aquifers, and ladies, I apologise, don't apologise for using the word man-made, I use it deliberately, because we can't blame women for this, okay? This is all blokes. So all of these highly permeable features, it's all blokes' fault, basically. The ladies were not involved, and women are not to blame for this. It's a man-induced problem, like so many others. But we've got highly heterogeneous permeability. We've got mine connections all the way to surface, bringing fresh recharge in one place, transmitting it rapidly through a major roadway or through areas of collapsed strata and so on, relaxed zones above the collapses and so on. Very heterogeneous, very dynamic, very permeable, much more so than a lot of natural aquifers. It's very interesting to work on. This is what I've spent most of my career working on, these artificial aquifers created by coal mining. Now, in the 20th century, most of the mining was by longwall. And this involves creating panels about 250 metres wide by about 1 kilometre long, in which we have total extraction. And I'll show you how that's done in a moment. But we take all of the coal out and we let the roof fall. Okay? So you're taking out 2 or 3 metres of coal, and just there, the roof is caving in. When the roof caves in, fractures propagate, in some cases 60 metres the seam thickness, up into the overlying strata. Okay? This is serious fracturing. This is much more than any shale gas fracking could ever do. Okay, shale gas fracking is puny in comparison to this. Really puny. In fact, I go so far as to say, as a Geordie, shale gas fracking is for pansies. If you really want to fracture some strata, do longwall mining. So how we do it, we set out a couple of roadways, or how we used to do it very recently. We put a tunnel across here in the coal, and then we shear back and forth with a shearer. And this is the current position of the shearer here. We have automated face supports that move this away. And behind the face supports, we just let the roof fall, and it falls and it forms a thing called goaf, from the Welsh word ogof, which means a cave. So we let it cave in, and the roof above it fractures to bilio. Here's the drum shearer at the end of a face about to be turned around. These are the last row of the supports. This particular photograph is in a mine I did a lot of work in, the second last working mine in Northumberland. And at this point, we're only 100 metres from a mine that's completely flooded to surface, and we're 400 metres below ground. And yet we're doing complete extraction of the coal, and we didn't get a drop of water into our workings. You would think you're all going to die, right? Certainly if you believe what you read in the press about fracking, you're definitely all going to die. We're 100 metres from a mine that was flooded catastrophically in the 19th century because they hauled into a peat bog. The peat bog liquefied and filled the mine, killed a bunch of people. And the mine was left flooded ever since. We're 100 metres from that doing total extraction mining. And as we move the face supports, the roof comes down. That's your goaf forming, right? That's fracturing, right? That's proper fracturing. Not this half-baked stuff down a borehole, with a magnitude of 0.5. These are 3.5 local magnitude events sometimes, right? You really hear them, you really feel them if you're in the mine. Stood on the face, it's terrifying, right? That's proper fracturing, right? That's Geordie and Yorkshire and South Wales fracturing, not this half-baked, puny hydraulic fracturing. It's nothing. That's puny. We don't just have one panel in a mine. Typically, we have a whole bunch of them. So this is going on at a big scale, covering many square kilometres. And there's a real science of the fracturing above it. We've got this zone that fills with a goaf. Then above that, we've got extensional fracturing. We've got a narrow zone of compressional fracturing, another distal zone of extensional fracturing, and so on. Studied very carefully, because the way we managed to survive 100 years mining as close as 105 metres to the bed of the North Sea without ever a drop of seawater coming into the workings, without ever drowning anybody with longwall mining, is that we always kept this zone of compression between us and the seabed, or between us and the overlying aquifer. Okay, so there's a lot of rock mechanics went into this, and this model served very well, not just to keep us dry, but to save us from drowning. So that's how I could be on this collapsing face 100 metres from a flooded mine and not die, because we know how the strata fracture. And this is far more intense than anything fracking could do. So we have this rule that if the net tensile strain at the base of the nearest overlying aquifer is less than about 10 millimetres per metre, then you're probably not going to have much hydraulic connection worth worrying about. If it's greater than that, you probably are. But you can see how close you have to get to exceed this threshold. Yeah, you've got to be really close for that fraction to interconnect to the aquifer on a scale of tens of metres. Not hundreds of metres, certainly not thousands of metres. Yeah? Tens of metres. And in fact, we exploit that relationship to move to short wall. If we're mining close to an overlying water body for some reason, we narrow the panels down to maybe 30 metres. And we'll come on to this in the Selby example in a minute, where we don't want to induce fracturing into an overlying aquifer. So, when the mine is abandoned, what do we have? Well, we've got two categories of mine, okay? This is the rarer category, but this is a category that Selby represents, okay? So this is a deep mine that's unlikely to give rise to pollution after abandonment and flooding, because all the workings are down here at great depth, okay? In this scenario, there's no connection to shallow old workings at higher elevation. There's only minor local water inflows to the deep mine workings during mining. And there's no scope for development of through flow conditions from a recharge area to these shafts after abandonment. Now, the cases I've shown you of all this horrendous water gullering out the ground, that's a different case. But it's the more common case in the UK with our long history of mining. So a deep mine that is likely to give rise to pollution after abandonment and flooding is like this. We've got direct connection to shallow old workings up dip at a higher elevation. There's brisk recharge of rainfall into these old workings. That drains down dip to the active workings. And after abandonment, through flow conditions are going to develop from this recharge area to these shafts at a lower level, and we're going to get an overspill. Okay? So, during mining, we've got the fresh recharge like that. It's coming down dip like this. It's being intercepted by pumps in the working mine down here, and that's how we keep the workings dry. Not unlike shale gas, where you've got to keep it pumped out to get the gas. We've got to keep the thing pumped out to get the coal, but also to get the gas, actually. If you let the thing float up, the gas switches off. The gas hazard goes. And, you know, there's all sorts of stories we could tell. After abandonment, what happens is the pumping stops here, but the recharge continues here, right? So without the pumping here, this is what happens. It backs up. The water spills out the shafts, the orange mess that I showed you before. Okay, so we know fine what happens. We know fine the circumstances that lead to pollution from these deep subsurface activities. Okay, we have shafts up to 1,000 meters deep doing this in places. So we know how this happens. But I'm now going to run you through the case of the Selby coalfield. This is the former friction winder, basically the heapstead, as we call it, the surface buildings of Wistow mine in the Selby coalfield. So at Selby, there were 5 pairs of shafts: Wistow, Stillingfleet, Rickall, Whitemoor and North Selby, increasing depth that away. All of these were just for man riding and materials, and all of the coal was produced by this inclined tunnel here, which surfaced at a place called Gascoigne Wood. And it was completely surrounded by trees and was a railway site, and most people didn't know it was there. And to get the coal from the deepest part of the mine to surface there was the equivalent of running a coal train. It was all conveyor belts, actually. It was the equivalent of lifting coal from Carmarthen to the summit of Snowdon. That's more or less what this inclined drift did. So a little bit about the history of the coalfield, okay? It was a very young coalfield. It was worked over 21 years. It was started in the mid-70s in response to the 1973 Middle East oil crisis. It was worked from 1983 to 2004. under a total area of 285 square kilometres. This is pretty big compared to what the reach of an individual shale gas operation would be. Yeah? 5 pairs of shafts, as we've said. Almost all the workings were in a single seam, the Barnsley seam. And crucially, the seams here are geologically isolated from those elsewhere in Yorkshire. So there's no possibility of connectivity to old shallow workings. None. No possibility of that. Peak annual production about 12 million tonnes, and over its life it produced 121 million tonnes. That's a lot of coal. That's a hell of a lot of fracturing. And as I'm about to show you, it's right underneath major aquifers. Okay? Sherwood sandstone's one of the major aquifers in all of the UK, heavily used in this area for drinking water and irrigation and industrial purposes, and crucially for brewing Sam Smith's beer. At greater depth still, the upper magnesian limestone, the lower magnesian limestone, the basal Permian sands, again, less prolific aquifers, but still important, and near outcrop, again used for brewing and so on. And here's the Barnsley seam, and you can see that there's a truncated anticline in the coal measure, so it's actually cut off by an unconformity at the base of this sand body here. So this does not connect to the rest of Yorkshire. It's an absolutely isolated bit of the Barnsley seam that then continues forever out under the North Sea. But just here, it's isolated from the rest of Yorkshire. Sinking the shafts through those overlying aquifers was a tough job. So here's the aquifers that we just mentioned on the cross-section. To get through this, they had to use ground freezing. Okay, so you drill a bunch of wells, you freeze the groundwater, you sink the shaft, you put in a reinforced concrete liner, then you can let the freeze go and not a drop of water will come into the shaft. I inspected all of these shafts before closure. After 20 years of use, these shaft liners were in absolutely perfect nick. And again, we could talk all night about that. You can see that the shafts got deeper from west at Wistow to northeast at Selby. So the deepest 1,033 metres. At that point, the nearest freshwater aquifer, well, it wasn't really fresh there, but anyway, the nearest prolific aquifer was about 500 or 600 metres above it. There was much closer a sandstone in the coal measures that could give nuisance quantities of water, but wasn't a freshwater aquifer, didn't outcrop anywhere. But, groundwater was a significant risk to the mining operation. It's the point I wanted to make. And this, in particular, the Sherwood sandstone's a major, major aquifer. Okay? So this is a good test for whether you can do this sort of fracturing at these sorts of standoffs of a few hundred metres without flooding the mine and killing everybody and without leaving a legacy of pollution of the overlying aquifer. So a really good test of that. So the parts of the seam that were worked from within about 80 metres of the base of the Permian in Wistow down to hundreds of metres in North Selby. So the shaded areas, what was actually worked. And the 3D perspective diagram, here's the inclined drift going down, the different pairs of shafts for the man riding and materials. All the coal comes out here. This is a little view inside the Gascoigne wood drift with the coal running up it in the late 1980s. And this is a summary of the panels that were worked. Now, there's an interesting thing here that these light-coloured panels here, these were short-walled. Do you remember that? If you're near an aquifer, you make the panels short. If you're far from an aquifer, you make them long. Okay? So most of it was long wall, and they went to short wall here because they were quite close to the aquifer. Okay? So again, interesting case. What was the mine water experience? Well, as I've said, they had to sink the shafts using ground freezing. Most of the workings were much more than 100 metres from the nearest aquifer and were worked by longwall methods with negligible water inflow. In fact, there was so little water inflow, they had to drill boreholes at surface into the overlying Sherwood sandstone's aquifer to get water for dust suppression and firefighting and take that water underground in pipes. There wasn't even enough water coming in to be handy, So they had to bring water in to keep the pit working and safe. That's how little water was coming in. So here are some typical longwall panels in the Stillinfleet area. You can see about 250 metres wide by a kilometre or so long. You can see how many of these there were. Vast. I mean, show a diagram to this, like this, to anyone and say you're going to frack an area of that size, they'll have kittens, right? But we've done all of that. Worked example, being done, not a drop of water from the aquifer, okay? The only water, some sodium chloride water, quite like flowback waters. Shallower, At Wistow, some of the faces, as I said, were as close as 80 metres to the overlying aquifer. And early doors, they got some significant temporary inflows. And so they changed the panel design to go to short wall. And then after that, the problems went away. And as they went deeper down dip, they went back to long wall. So this is just a map showing the very narrow panels of Wistow. So a lot of these only 30 metres wide, okay, that we used because they were close to overlying water bodies. But there was no impact on the piezometry of those overlying water bodies, none at all. It was just a nuisance to the miners. And none of it was ever fresh water that they intersected. But as I say, once they shifted to short wall, problem solved. Eh? Yeah, I'm nearly done actually. Yeah, I'm nearly done. Here's the total water make of the Selby coalfield, about 19 litres per second. That might sound like a lot of water. You certainly wouldn't want that in your living room. Okay? But this is over 285 kilometres squared. Okay? Put it in perspective. From mine systems that drain a similar area, couple to 300 square kilometres, here are the water makes, averaging 155, peaking at 300. And when you compare that, Selby is definitely puny, okay? Because it's not connected up dip to old workings. All of them are. If you're connected up dip to old workings, you've got a lot of water. If you're not, negligible. Put that another way, in megalitres per day per square kilometre of coalfield. Average from all these coalfields around the world, 0.31. Selby, 0.006. Okay, it's nothing. It's really nothing. Post-abandonment then, what do we expect for Selby? Most water entering the Selby workings before closure was sodium chloride water, typical of long-term storage in the local coal measures. Such inflows are head dependent. We always find that as the mine floods up, they'll be eliminated. The residual inflow is going to be something like 0, but the maximum estimate we would have would be about 11 litres per second over the 285 kilometre squared area. In other words, about 1% of the rate of fresh groundwater moving through the overlying Sherwood Sandstones aquifer. It's really negligible. The flooding of workings will be very slow. Even now, there's no sign of the water getting to the foot of any of the shafts. There's no up-dip connection to the shallow old workings. Therefore, there's no future mine water outflows anticipated. So Selby corresponds to this case we saw before of a mine system that's extremely unlikely to give rise to pollution after abandonment and flooding. So here's the punchline you were waiting for. We've already seen this diagram. Let's draw the same one for shale gas. That's what shale gas does. Not as much fraction, okay, much smaller. Similarly, no connection to shallow aquifers at a higher elevation. Only minor local water inflows to the shale gas wells during production. No scope for development of through flow conditions from recharge areas to boreholes after abandonment. And go back to a point I made right at the start of the lecture, in any case, the depth is about twice that of the deepest mine at Selby. There's no problem at North Selby mine. Why would there be a problem at twice the depth with far less fraction? Doesn't make sense, because it's nonsense. Nonsense tends not to make sense. So here's some take-home messages. Fracking is puny compared to the fracturing wrought by longwall mining. Absolutely puny. It's not for, it's not really for real men, fracking, If you want to really fracture some rock, do longwall mining, Longwall mining is being undertaken routinely as close as 105 metres to major aquifers in the seabed with no hydraulic connection development. Short wall and non-caving mining can approach even closer without inducing hydraulic connection. Shale gas fracking is planned to be 10 to 20 times further below aquifers than this. 10 to 20 times further. Shale gas companies in any case have a vested interest in avoiding creating hydraulic connections, and the lack of a driving head during and after gas production means assurance is doubly sure that no post-abandonment pollution can occur. However, we'll not leave it totally to chance. We've got a live demonstration in a country that's not yet abandoned the Enlightenment, Poland. We're part of an international consortium, and what we're doing there under this project, you can look it up. The Polish government is taking a more sensible attitude to shale gas. They're saying, let's find out if there's any shale gas there before we get all excited. So they're drilling wells and fracking them. So there's two 2 wells being drilled on this site to a depth of 2 kilometres with 1 kilometre laterals going in different directions. Our job has been to install groundwater monitoring in the very prolific freshwater aquifer at surface and to see what happens when they frack these, which they're going to do very soon. It's going to be the most boring groundwater data set I've ever collected. It's going to be as tedious as can be, but what the hell, it gives some work to one of my very able postdocs. So if you believe what I've said, and I hope you do, what does that leave in terms of what are the real risks of shale gas fracking? So this is the final slide I promised you. Leaky well casings, well, these are illegal actually for safety reasons because of the risk of gas leak, so they're very heavily regulated in the UK. I don't see much scope for that. Surface spillages, well, this is no different from any other industry. We have a very good, mature regulatory system that militates against that with double bunding of anything you're worried about and so on. Though not thanks to Dick Cheney in the United States, so a very different regulatory system. Noise, I have to tell you that modern drilling rigs are so quiet that the drill crew don't even have to wear ear defenders. When I've been drilling deep wells in central Newcastle, 100 metres from the nearest house, to drilling geothermal wells with the very same rigs that are used for shale gas, the council noise inspectors come and say, we've come to monitor your noise. Right, great, welcome lads, crack on. Well, can you please crank everything up to the maximum velocity so we can get a good measurement? I said, this is the maximum velocity. This is all it is. Nobody on the drill floor even wearing ear defenders. You know, so this is not like a pneumatic drill on the pavement. This is, you know, it's very well acoustically insulated. Traffic. That's the big one, I think. Huh? Urban air quality, traffic movements. And look, I'm a cyclist, and when I'm not cycling, I travel on public transport. Let's ban heavy traffic. I don't mind. Let's get rid of it for all purposes. Let's not single out one industry. It's been estimated by my colleagues in Strathclyde University that the traffic movements at a peak of a major shale gas site would be about the same as the traffic movements for a Tesco Extra. I happen to cycle past the Tesco Extra most days. I've not actually seen many of the heavy vans going in there, but I would happily close it down anyway, out of spite for heavy vehicles when I'm cycling. So get rid of it all and see if I care. So the question, can these risks be effectively managed? Well, we answered this 4 years ago. All I've done is amplify the answer. Yes, as long as the operational best practices are implemented and they're using the regulatory framework we've got. Pay attention to how the risks may scale up. In other words, if you've got a Tesco Extra here and a Tesco Extra there and a Tesco Extra there, the risks are going to scale up. You've got to keep an eye on that. But to summarise, nothing significant's been done in the UK to wean us off gas use. It's our main source of heating and electricity production on demand. As offshore production declines, we either import more or develop indigenous sources. The source pathway receptor modelling that I talked about and the large-scale example of the Selby coalfield both demonstrate that the thing we need worry about least is the exotic deep subsurface activities. The stuff we really want to worry about are the mundane surface activities that our planning system deals with all the time. So my view on the hydrogeological aspects of the fracking furore is that. Thank you very much. Sorry I overran, but we seem to be enjoying it.
Thank you very much, Paul. As a geologist in the mining industry, I certainly enjoyed that analogy. It helps me to be able to explain it to others as well. If we have any questions, could you please wait for the microphone because we're being recorded. Would anybody like to start? I'm down here.
Could I ask, please, about the pollution risks of the water that's taken out of the wells? And what are these biocides and what are the risks from these chemicals?
From the flowback water?
Yes, from that.
Yeah, I mean, the biocides are used in the injected water. That's basically like chlorinating water. Okay, so if you've got chlorinated tap water, you wouldn't add the biocides. So it's about as dangerous as chlorinated tap water in your tap. So if you're worried about biocides, worry about chlorine in your tap. The flowback water, the big issue is simply the salinity. You cannot put water as saline as that into a freshwater course. No way. So either it's going to be recycled in the process for later fracks, or it's going to be treated, probably reverse osmosis, or tankered to somewhere where it can be put through reverse osmosis. It simply wouldn't be allowed to release water as salty as that to any freshwater course. It's just illegal. So it's just salty water. It'd be like if you suddenly got a tanker full of seawater in the middle of the country. A good idea is not to let it down the nearest brook, because the chances of the local fish evolving to be marine species over the time it takes for you to pour it in there is very small.
I understand that in the case of the US fracking industry, there was some concern as recently as a year or so ago that production from the rigs would tail off very quickly, would fall away very quickly, which in the event hasn't proved to be the case. But how much knowledge do we have in terms of the longevity of production from these rigs?
I mean, it's still relatively early doors. You do get an exponential decline in gas production. So they definitely produce a lot more at first, and that tails off. And you can sometimes refract the wells, but it doesn't get you anything like back to the original rate of production. It lifts it a bit and prolongs the tail. So it does tail off. But you know, the industry's not been really round long enough for us to have a glib global answer for, you know, what's the average for one of these wells in a given formation becoming unviable. I mean, it may well be that despite some of the formations in the UK looking prospective for shale oil and gas, they may not be that productive anyway. So this might be all a typhoon in a teacup for now anyway. You know, we really won't know until we do what the polls are doing and actually try it properly under controlled conditions.
Sorry, my voice is very low. How much fracking has been done in offshore UK already?
Oh, it's routine. I mean, yeah, it's as the conventional oil and gas fields mature, almost all of them are going to have some degree of fracking to improve the yield during the long tail. You know,
so we have quite a bit of experience already.
Absolutely, yeah, and onshore. I mean, you know, there's been about 200 wells fracked onshore. One I document in the paper is Salisbury, right near the junction of the M73 and the M8 near Glasgow. Fracked in 1963, produced gas for a decade or so, and then properly abandoned, cemented up. You know, not a problem. So, you know, this has been done before, but for some reason we seem, you know, determined to forget history, and that's why I went to the bother of documenting the Selby coalfield, because I've still got the notes and I could do it, but when I shuffle off this molten coil, probably my sons, because none of them are scientists and engineers, I just hoy them out.
Any further questions? One more again.
How much deep geothermal experience do we have in the UK?
Very little. There's so you're looking at the only person who's drilled any deep geothermal wells in the UK since the turn of the millennium. I've drilled 3. Nobody else has drilled any yet. Before that, there was some drilled in the 70s into the mid-80s, but only one of them has ever put into production. This was the one at Southampton. The one that we drilled in Eastgate is an excellent resource, but unfortunately we managed to coincide finishing the testing with the global financial meltdown, followed shortly after by the abolition of the Regional Development Agency, who were driving the project to build the heat demand for us. So it'll happen sometime, but taking a while. The waters are very similar to the ones we've been describing as flowback waters, sodium chloride, some radon in them, some naturally occurring radioactive materials. So we had to be very careful with what we did with those waters, because we're right next to the River Wear, major trout stream. So.
Any more questions? Okay, if we could please put our hands together for an
Thank you very much. Well, we did early doors, and occasionally we get the odd follow-up from the Joint Royal Academies thing. I mean, the Scottish government very cynically pretended that they've got